Good morning, students. In the previous class, that is class 3 of the chapter Electrochemistry, I completed electrolytic resistance and conductance, specific conductance, equivalent conductance, molar conductance, relationship between equivalent conductance, specific conductance and molar conductance, and some problem relating to it. Today, in class 4 of the chapter Electrochemistry, I will try to complete how the equivalent conductance, molar conductance and specific conductance varies with dilution. Next, law of independent migration of ion, that is Collard's law, application of Collard's law. Next, electrochemical cell or galvanic cell, the definition, construction, working principle, observation and salt bridge, function of salt bridge and the cell notation or cell representation. So before going to the today class, let us recap about the previous section. That means, what is Ohm's law? Ohm's law, the mathematical expression is the strength of the current I is equal to V by R. I, strength of the current expressed in ampere. V, potential difference in volt. R, resistance in ohm. Next, conductance, that is mathematically the reciprocal of resistance. Then, specific conductance. Then specific conductance kappa, specific resistance rho, they are interrelated with some formula, that is C is equal to 1 by R, that is conductance is equal to reciprocal of resistance. Next, R is equal to rho into L by A. Rho is a proportionality constant that is known as specific resistance or resistivity, or rho is equal to R into A by L. Next, kappa is equal to C into L by A, where kappa is another constant that is known as specific conductance, which is the inverse reciprocal of specific resistance. C is the conductance, and L by is another constant that is known as a cell constant. Next, equivalent conductance, that is kappa into 1000 by normality. Molar conductance, that is kappa, specific conductance into 1000 by molarity. And the relationship between them, that is molar conductance by equivalent conductance, that is normality by molarity, that is known as valency factor. What is a valency factor? That is, it is the acidity of a base, basicity of an acid, and for a salt, that is the total valency of the metal atom. These are some terms. Next we discuss about the unit of this one, resistance, that is in ohm, conductance, that is in ohm inverse. In SI system, it is known as a Simon. Next, that is specific resistance, unit is ohm centimeter. That is specific conductance, that is ohm inverse centimeter inverse. The equivalent conductance unit is ohm inverse cm square gram equivalent inverse. Molar conductance, that is ohm inverse cm square mole inverse. These are the units of the different mathematical expression. Next, today we discuss about how equivalent conductance, molar conductance and specific conductance vary with dilution. Mark that. Dilution, on adding water to a larger quantity, degree of dissociation, degree of ionization takes place, forming more number of ions. If number of ion increases, then ionic conductivity increases. Hence, on increasing dilution, equivalent conductance and molar conductance increases. On the other hand, specific conductance decreases with increasing dilution, because as per the definition, on increasing dilution, the number of ions present in 1 cube of a volume decreases. So, we draw one conclusion that on increasing dilution, equivalent conductance and molar conductance increases while specific conductance decreases. Next we discuss about very important 3-mark question. It may be 2 mark or 3 mark. If it is 2 mark, means state law of independent migration of ion or Molar's law. On the other hand, if it is 3 mark, then question is write short notes on law of independent migration of ion. So now switch over to law of independent migration of ion, that is known as Molar's law. Next is law of independent migration of ion. Law of independent migration of ion, otherwise known as Molar's law. What is this law? This law states that the limiting molar conductivity of an weak electrolyte. What do you mean by limiting molar conductivity? Means molar conductivity of a weak electrolyte at infinite dilution. I repeat again. This law states that the limiting molar conductivity of a weak electrolyte is equal to sum total of molar ionic conductivities of cations and anion, and each multiply with number of cations and anion present in one formula unit of the electrolyte. I repeat again, this law said that the limiting molar conductivity of a weak electrolyte means molar conductivity of a weak electrolyte at infinite dilution is equal to sum total of molar ionic conductivities of cations and anions, and each multiplied with the total number of ions present in one formula unit of an electrolyte. Mark that. This law said that the limiting molar conductivity of a weak electrolyte. What do you mean by limiting molar conductivity? Means molar conductivity of a weak electrolyte at infinite dilution is equal to the sum total of molar ionic conductivity of cation and anion, and each multiplied with the total number of ions present in one formula unit of an electrolyte. Mathematically, this law may be expressed as, represented as, if we select weak electrolyte, that is AXBY, then molar conductivity at infinite dilution of weak electrolyte XBY is equal to X into molar conductivity of cation, Y into molar conductivity of anion. It is a mathematical expression of law of independent migration of ion. Mark that. This one XBY is known as the weak electrolyte. Here, this term, these two terms, that is molar conductivity of cation, it is known as molar conductivity anion. Which one is cation? Cation, the formula unit of cation is A to the power Y plus, it is known as the cation. While B to the power X minus, it is known as the anion. And it is known as the number of cation, it is known as the number of anion. It is the mathematical expression of Coulom's law. If we apply it to a particular electrolyte, let us consider mark that. If we consider first example, molar conductivity at infinite dilution of sodium chloride is equal to molar conductivity at infinite dilution of sodium ion plus molar conductivity at infinite dilution of chloride ion. If we select another example, that is molar conductivity at infinite dilution of magnesium chloride, then it is molar conductivity at infinite dilution of magnesium ion plus 2 into molar conductivity at infinite dilution of chloride ion. Similarly, if we go through another example, molar conductivity at infinite dilution of aluminium sulfate Al2SO4 whole thrice, that is 2 into molar conductivity at infinite dilution of aluminium ion plus 3 into molar conductivity at infinite dilution of sulfate ion. This is the application of Coulom's law to a particular electrolyte. Then we discuss about the application of Coulom's law. Next, we discuss the application of Coulom's law. That is application. 3 applications are there. Point 1. Calculation of molar conductivity of weak electrolyte at infinite dilution. Point 2. Calculation of degree of dissociation. Point 3. Calculation of dissociation constant. That is, point 1 is calculation of molar conductivity of a weak electrolyte at infinite dilution. Second one, calculation of degree of dissociation, degree of ionization or degree of dissociation, symbol alpha. Third one is calculation of dissociation constant. Calculation of dissociation constant or ionization constant, that is K. These are the 3 applications of Coulom's law. Let us discuss one by one. First one is calculation of molar conductivity of weak electrolyte at infinite dilution. By definition of a weak electrolyte, we know that is a partially ionized, weakly ionized. That means that electrolyte not completely ionized to form exact amount of cation and anion. So experimentally also it is difficult to predict the molar conductivity of an weak electrolyte at infinite dilution. But by the application of this law, one is able to calculate the molar conductivity of an weak electrolyte at infinite dilution indirectly. For example, let us consider the case of acetic acid. It is an weak electrolyte. So, in order to calculate the molar conductivity of weak electrolyte at infinite dilution, we have to select the 3 strong electrolyte whose value calculated experimentally. So we have to select 3 strong electrolyte in such a way that by addition of 2 and subtraction of last one give the result. For example, mark that molar conductivity at infinite dilution of acetic acid can be calculated by taking molar conductivity at infinite dilution of sodium acetate plus molar conductivity at infinite dilution of hydrochloric acid minus molar conductivity at infinite dilution of sodium chloride. Mark that when this one ionizes, it gives rise to acetate ion, molar conductivity at infinite dilution of acetate ion, molar conductivity infinite dilution of sodium ion plus molar conductivity infinite dilution of H plus ion plus molar conductivity infinite dilution of Cl minus ion minus molar conductivity infinite dilution of sodium ion minus molar conductivity infinite dilution of chloride ion. Mark that. This one cancel, resulting the formation of molar conductivity acetate ion and molar conductivity H plus ion, which is nothing but the molar conductivity of acetic acid. So let us apply this concept to solving one type of problem. Mark that. What is the question? Molar conductivity at infinite dilution of sodium acetate, sodium chloride and hydrochloric acid are 298.3, 103.3 and 109.4 mole inverse Cm square, ohm inverse, Cm square, mole inverse respectively. Calculate molar conductivity of acetic acid. Mark the question. It is we have to find out the molar conductivity of acetic acid, that is weak electrolyte. its value never calculated experimentally. For that, we have to choose indirect help of Molar's law. So for that, we have to select three strong electrolyte. One is known as sodium acetate, one is known as sodium chloride, and one is known as hydrogen chloride. Just before we mark that is molar conductivity at infinite dilution of acetic acid is equal to sum total of molar conductivity of sodium acetate plus molar conductivity at infinite dilution of hydrogen chloride minus molar conductivity at infinite dilution of sodium chloride. Mark that. Sodium acetate value is given, hydrogen chloride value is given, and sodium chloride value is given. So put this value, add this value, that is sodium acetate value is 298.3 plus hydrogen chloride, that is 109.4 minus 103.3 ohm inverse Cm square mole inverse. The result is, that is molar conductivity at infinite dilution of acetic acid. So you go to another type of problem. Next question is question number 2. Molar conductivity at infinite dilution of barium chloride, sodium hydroxide, and sodium chloride are 108.2, 305.8 and 77.8 ohm inverse Cm square mole inverse respectively. Calculate that of barium hydroxide. Mark the question. The barium hydroxide weak electrolyte, its molar conductivity at infinite dilution can be calculated indirectly by the help of Molar's law by taking three strong electrolyte. These are given in the question. One is known as barium chloride, one is known as sodium hydroxide, one is known as sodium chloride. Mark that. We have to deduce one relationship among them, that is answer. Molar conductivity at infinite dilution of barium hydroxide is equal to molar conductivity at infinite dilution of barium chloride plus 2 into molar conductivity at infinite dilution of sodium hydroxide minus 2 into molar conductivity at infinite dilution of sodium chloride. Let us verify. Mark that. This one equivalent to molar conductivity at infinite dilution of barium ion plus 2 into molar conductivity of chloride ion plus 2 into molar conductivity infinite dilution of sodium ion plus 2 into molar conductivity at infinite dilution of hydroxide ion minus 2 into molar conductivity at infinite dilution of sodium ion and minus 2 into molar conductivity infinite dilution of chloride ion. Mark that. 2 chloride minus cancel out, 2 sodium cancel out. then molar conductivity of barium ion, and 2 into molar conductivity of hydroxide ion, which is equivalent to molar conductivity of barium hydroxide. So, molar conductivity of barium chloride value is given, molar conductivity of sodium hydroxide given, and molar conductivity of sodium chloride given. Add these two values and subtract the third one, give the result. Move to another type of problem. Next question. Molar conductivity of aluminum chloride, at infinite dilution is 204.32 ohm inverse cm square mole inverse, and that of chloride ion, that means molar ionic conductivity of chloride ion is 101.02 ohm inverse cm square mole inverse. Calculate the molar ionic conductivity. Calculate the molar ionic conductivity of aluminum ion. Mark the question. What are the data? Molar conductivity of aluminum chloride is given. That means answer. Molar conductivity at infinite dilution of aluminum chloride is equal to molar conductivity at infinite dilution of aluminum ion plus 3 into molar conductivity at infinite dilution of chloride ion. By definition, its value is given. That means 3 into molar conductivity, molar ionic conductivity of chloride ion is equivalent to molar conductivity at infinite dilution of aluminum chloride minus molar ionic conductivity of aluminum ion. So its value is given in the question. Question is calculate molar ionic conductivity of chloride ion. So molar ionic conductivity of chloride ion is equal to this value into 1 by 3. Putting this value, these two, reduce this value and multiply into 1 by 3. One is able to calculate the molar ionic conductivity of chloride ion by using this law. Next switch over to second application. What is the second application? Second application, that is calculation of degree of dissociation or degree of ionization. Symbol is alpha. How we calculate indirectly by the help of this law. Mark that. What do you mean by degree of ionization? Mark that. The fraction of molecule dissociated divided by total number of molecule taken. So how you calculate this one? One mathematical expression is there. That is alpha is equal to molar conductivity at a particular concentration by molar conductivity at infinite dilution. Mark that. This term is known as molar conductivity molar conductivity at a concentration C, and this term is known as molar conductivity at infinite dilution. So if this value are given, by dividing, one is able to calculate the degree of dissociation or degree of ionization of a weak electrolyte. So let us apply this formula to solve one type of problem. Question: the molar conductivity of 0.1 m acetic acid solution is 32.3 ohm inverse cm square, and the molar ionic conductivity at infinite dilution of acetate ion and hydrogen ion are 103.4 and 98.7 ohm inverse cm square respectively. These are per mole. Calculate the degree of ionization. Mark the question. What are the data given? Data given for a particular concentration. For a particular concentration, molar conductivity of weak electrolyte, that is acetic acid, is given. That is answer. Given that lambda mc, that is molar conductivity at a particular concentration for acetic acid, is given 32.3 ohm inverse cm square mole inverse, and that of infinite dilution of acetic acid direct not given, rather infinite dilution of acetate ion and H plus ion is given. That means molar conductivity at infinite dilution of acetic acid is equivalent to molar conductivity, ionic conductivity of acetate ion and molar ionic conductivity of H plus ion. These two values is given, means one is able to calculate the molar conductivity at infinite dilution of acetic acid. So the formula is, what is the formula? Alpha is equal to molar conductivity at a particular concentration divided by molar conductivity at infinite dilution. So this value is given in the question. Now you calculate this value. Dividing this one is able to calculate the degree of dissociation or degree of ionization. Move to the third application. What is the third application? That is third application, calculation of dissociation constant. Calculation of dissociation constant, that is K or Kc. After knowing the concentration, after knowing the degree of dissociation for a weak electrolyte at infinite dilution, One is able to calculate the degree of dissociation, that is dissociation constant or ionization constant, by the formula that is K or Kc is equal to C alpha square by 1 minus alpha, where C is known as the concentration and alpha is known as the degree of dissociation or degree of ionization. Next, let us solve this formula for using how this formula is utilized for solving a problem. Question 8291 Kelvin. The molar conductivity of acetic acid at infinite dilution is 107.23 ohm inverse cm square mole inverse, and its centinormal solutions molar conductivity is 56.23 ohm inverse cm square mole inverse. Then calculate the degree of ionization and also the ionization constant and also ionization or dissociation constant. Mark the question. First we have to calculate alpha, degree of ionization. Next we calculate the dissociation constant. The formula is K or Kc is equal to C alpha square by 1 minus alpha. Mark that. For that we have to calculate the alpha. We know alpha is known as molar conductivity at particular concentration by molar conductivity at infinite dilution. So molar conductivity of particular concentration given, molar conductivity at infinite dilution given. By simply dividing, one can able to calculate the degree of ionization or degree of dissociation. Putting this value, that is centinormal solution concentration given, degree of ionization, degree of dissociation given. So by putting this value, one is easily calculate the dissociation constant or ionization constant. This is all about the application of law of independent migration of ion or Molar's law. In class 1 of the chapter electrochemistry, that means in introduction class already covered, the electrochemistry is based upon two fragments. One fragment, that is electrical energy converted to chemical energy, that is known as electrolytic cell, part is over. Now discuss about chemical energy transfer to electrical energy, that is electrochemical cell or galvanic cell. So now convert to galvanic cell or electrochemical cell. Next is electrochemical cell or a galvanic cell. Mark that. It is a device in which chemical energy, that means indirect redox reaction takes place as a result of which production of electrical energy. It is a device in which chemical energy converted to electrical energy. This is known as galvanic cell or electrochemical cell. The chemical energy means indirect redox reaction. What is redox reaction? Oxidation and redox reaction move simultaneously. What do you mean by indirect redox reaction? That means oxidation and redox reaction carried out in different container. So it is a device in which indirect redox reaction takes place as a result of which decreasing free energy is converted to electrical energy. That device is known as electrochemical cell or galvanic cell. I repeat again, it is an instrument, it is a device in which indirect reduction reaction takes place as a result of which decreasing free energy converted to electrical energy. Now we go through the construction of this cell, working of the cell, then principle, theory and cell notation. Mark that. First we go through the construction. Construction of the cell. This cell consists of two half cells, two different beakers. One zinc rod, one copper rod, some insulated copper wire, connecting wire, one ammeter or voltmeter to identify the flow of current. Next, one inverted U-shaped glass tube known as salt bridge. Mark that how they are interconnected. This one is known as left half side, that is one half cell, it is known as another half cell. So mark that. One container, that means in which 0.1 m zinc sulfate solution is taken, 0.1 molar zinc sulfate solution taken, in which zinc rod is dipped in the solution, and this is known as zinc half cell. And it behaves as anode, so otherwise it is also known as anode half cell. And next one is another beaker containing 0.1 m copper sulfate solution, and in which copper rod is immersed into it. And as it is known as cathode, it is known as cathode, it is known as anode. As it is known as cathode, otherwise also it is known as cathode half cell or copper half cell. It is known as negative, it is known as positive, otherwise it is also known as a negative half cell, it is also known as a positive half cell. And this one, the inverted U-shaped glass tube made up of inert electrolyte in agar-agar or gelatin. This is known as salt bridge. Mark that, it is the connecting wire. This is the cell representation. One half cell, left half cell, known as zinc half cell, right half cell is known as copper half cell. Next we discuss about observation. What do we observe? Next one is observation. What do we observe? When cell complete, zinc rod zinc rod loses its mass while copper rod gains its mass. Point 2. The concentration, that means zinc loses to electron and electron move from anode to cathode, that means zinc to copper, and the zinc becomes zinc ion. So zinc ion moves to here to the electrolyte, and this electron taken up by copper, this is copper ion, this is Cu2 plus ion, and by taking this electron move to there, as a result of which the weight of the zinc rod gradually decreases, the weight of the copper rod gradually increases. Then concentration of the zinc ion in the zinc half cell increases, and concentration of copper ion in copper half cell decreases. And there is a flow of electron externally, flow of electron nothing but the flow of current. And internally, the circuit is closed by the salt bridge, which maintain the electrical neutrality. Next we discuss working. Next is, third one is working. Mark that. When the cell reaction complete, when the circuit complete, what we observe? First thing is, from anode, zinc loses to electron and moves to the solution in the form of Zn2 plus ion. Means here oxidation takes place. So at anode, oxidation takes place. That's why it is also otherwise known as oxidation half cell. So mark that. What is oxidation half cell reaction? Oxidation half cell reaction, that is zinc solid loses 2 electron to form zinc ion plus 2 electron. It is known as zinc half cell reaction. The electron that is removed here is moved through the external connecting wire and is taken up by copper ion at cathode. So at cathode, reduction takes place. That's why it is also otherwise known as reduction half cell reaction. Mark that. Second thing is that is reduction half cell reaction. What is reduction half cell reaction? Copper ion plus 2 electron give rise to copper solid. When the cell reaction proceed for a long time, so this rod loses its weight while this rod gains its weight. And there is a flow of electron externally, and internally there is a flow. Here we select, that is what we select, that is known as salt bridge. What is salt bridge? Salt bridge is an inverted U-shaped glass tube made up of inert electrolyte like potassium chloride, ammonium chloride, potassium nitrate, potassium sulfate, etc. And is present in forming a jelly-like agar-agar or gelatin. And the mouth is blocked with a cotton. What do you mean by inert electrolyte? An inert electrolyte is one which not participate in the redox reaction as well as not react with the electrolyte. So what is the function of salt bridge? Next we discuss about function of salt bridge. Very, very important one. It is a 2-mark question. What do you mean by salt bridge? And write down its function. Mark that. Function of salt bridge. 3 to 4 points are there. Point 1. It connect the 2 half cell. Point 2. It complete the cell circuit. Point 3. It maintain the electrical neutrality. Next, it prevents the migration of electrolyte, movement of electrolyte from one half cell to the other. And last one is it prevents the liquid junction potential, very very important one. What do you mean by liquid junction potential? Mark that. When concentration of zinc ion increases, when concentration of copper ion decreases, so there is a development of a potential difference. As a result of which, automatically there is a flow of electrolyte. So in order to maintain the electrical neutrality, in order to maintain the potential difference, mark that. Here suppose we select potassium nitrate, that is K plus NO3 minus. So in order to neutralize the zinc 2 plus, the nitrate ion moves here. In order to maintain the Cu2 plus ion, the K plus move here. As a result of which, it is maintained the potential difference. As it is liquid, so it is known as liquid junction potential. It is allow only, salt bridge only allow the ion, not the electrolyte. This is the function of the electrolyte. Sorry, this is the function of the salt bridge. Next, we go through the cell representation. How symbolic representation of a cell takes place. The last one is the cell notation or cell representation. Next is cell notation or cell representation. Mark that. That is metal solid. Next is converted to metal ion and its concentration 0.1 m. Double vertical line, that is known as salt bridge. Then another metal ion 0.1 m. Molar concentration, metal in solid. Mark that. This is known as anode half cell. It is known as cathode half cell. It is known as salt bridge. Just now discuss anode is zinc and cathode is copper. Otherwise it is also known as zinc half cell. It is known as copper half cell. As here oxidation takes place, oxidation half cell. As here reduction takes place, it is known as reduction half cell. As anode is connected to the negative, it is known as negative half cell. Negative half cell, it is known as positive half cell. This is it is known as salt bridge. It is known as symbolic notation or symbolic representation of a cell. Last is known as cell reaction. How we represent the cell reaction? Last is, that is cell reaction. Never confuse cell representation and cell reaction. Symbolic representation of cell is known as cell representation. And what are the different type of reaction? Oxidation and reduction. Redox reaction going on, that is known as cell reaction. So two type of half cell reaction is there. One is known as oxidation half cell reaction. That means zinc solid give rise to zinc ion plus 2 electron. And the second one is reduction half cell reaction. That is copper ion gains electron give rise to copper solid. So if we add, that is net cell reaction is zinc solid plus copper, this one cancel, copper ion give rise to zinc ion plus copper solid. This is known as cell reaction. So mark that how indirect reduction reaction takes place. In anode half cell, oxidation takes place. In cathode half cell, reduction takes place. Mark that it is known as oxidation half cell reaction, and it is known as reduction half cell reaction. So in this way, the galvanic cell, indirect redox reaction takes place, as a result of which the decrease in free energy converted to electrical energy.